My name is Oh Kyung-Kwon, Professor Emeritus of Seoul National University of Korea. I'd like to introduce the plenary speaker, Dr. Peter Terwiesch. Dr. Peter Terwiesch is Chief Technology Officer of ABB, a global power and automation technology company with 117,000 employees and operation in more than 100 countries. Prior to his current appointment, he was the president of ABB Automation, Germany, at the same time as global head of technology for ABB's automation business. Peter holds PhD in electrical engineering from ETS Zurich, Switzerland. Manfred Morari was the examiner for his PhD committee. Also Master of Science in Engineering from Karlsruhe Institute of Technology, Germany, and is an alumni of Harvard Business School General Management program. As a scientist, he has contributed to a number of significant technology initiatives and has also authored and co-authored numerous papers and patents, mostly in the area of automatic control, signal processing, and energy efficient technology. Peter is serving on a number of the board and committee, including supervisory board of Matterjuk AG, the Control System Board Committee of IEEE, IEC Market Strategy Board, German Automation and Sensing Society, and number of other industry and industrial academic board and council. Topic of this plenary talk is closing the loop on industrialist perspective on present and future impact of the control. He will introduce both status quo and the future potential of the automatic control in industry. Conference organizer planned not to take any question after his talk for efficient operation of the conference, but the speaker will be happy to reply to any question during the subsequent coffee break so that he can fully use his time. We will turn on the light for videotaping. Let's welcome Dr. Peter Terwiesch for his talk.
Thank you, Professor Kwon, for the kind introduction. Mr. President Di Alberto, distinguished Ifac council members and officials, it's of course a great honor to be here, and also in a personal way close the loop on a subject that is very near to my heart and yours, of course. You wouldn't be here on automatic control. In 1993, I attended my first Ifac World Congress in Sydney then, for my PhD thesis, quite charged up on methods and the solution space, but was a rather vague notion then, I have to admit, on the control problem space. And in some sense, I've spent more time on the control problem side and on making the match to the solution world. So in some sense, I regard this presentation for which you have kindly invited me also as a personal opportunity to close the loop. I'm going to just briefly talk about some trends and drivers that I think underlie the different application areas that I will then go through: power systems, process automation, and robotics. And I'll also, towards the end, then conclude with some personal statements and outlooks that are deliberately a bit subjective, so you might actually disagree with some of them and have something to discuss with me or amongst each other during the coffee break. I think on this level of drivers, and I'll keep the generic ones short and rather take drivers then as we go to more practical examples. On this level of drivers, I think there's been a continued trend, and I'm deliberately reusing a slide to say I don't see a change in that trend, that the constraints and boundaries that we are faced with in industry and the utility space, they increasingly tighten, and the consequences of violating them are increasingly severe. This can be deviations in product quality, where you just don't get the price for the product that you were expecting, or this can also be, for instance, a violation of environmental rules, where the penalties are growing into dimensions where they deliberately become very painful. At the same time, as that's happening, the buffers everywhere are getting trimmed. This can be the inventory that sits in companies' warehouses with modern management methods, basically eliminating inventory, bringing down capital, is a major driver, all the way to plant design, where in order to have more flexible plants that tie up less capital, that are sort of faster to start up, shut down, change grade, everywhere there's more integration, which obviously not just accelerates the dynamics, but creates in itself a couple of interesting control challenges. Across all application spaces, and I really think beyond industry and utilities, but for us as a society also, in recent years we've all come to see as a common theme the energy challenge. I'm not going to spend a great amount of time on this slide, but basically by forces of market versus environmental considerations and security of supply considerations, every country, every company is finding its own optimum in the space, and events are certainly also contributing to a rebalancing in this triangle. If you look at energy efficiency from a high level, and I know that you don't need this simplification, but it's easy to put it here in short, then basically if you look at 1 unit of primary energy that is extracted and you push this through the energy value chain, at the end of that pipe you only get about 20% of useful energy, regardless of which specific path this takes. So there's losses at every stage of the chain. We know that there's no 100% efficiency, but it's quite surprising still if you put it together to see that 80% are lost along the way. And it's also fairly well known that at every stage there's a potential to improve this efficiency, which if you really look into it and zoom into that potential, I think technology can more than double the piece that makes it to the end, and I see control as really vital in unlocking those improvement opportunities at every stage. It can be through process control already in the extraction side, so in the oil and gas industries, the mining industries. It can be on the transport, where if you look at pipeline losses or other costs of transporting fuel, power generation, transmission and distribution. If people talk about smarter grids, as Paul Haupt will do later this week, of course this means actually grids with more control. I'll get a little bit into that also in this talk. Process control, energy management is also an industry word of saying control in many ways. And finally, the smart buildings also. So I think it's important for us as a community to see how much of our work in the application space is actually underpinned by this common energy challenge. At the same time, if I take the Ifac logo and group a couple of technology trends that underlie all application areas, then really on the sensing side, We are in the fortunate situation that sensors become more ubiquitous, and that's of course one essential prerequisite to close control loops. That is, you need sensing. They're becoming more affordable. There's a couple of new ones, and many of them are more information rich. I'm thinking here inline analyzers, for instance, in process automation, but I'm also thinking devices that have always measured pressure or temperature, but today actually have much enhanced functionality, so that, for instance, they can filter information about their own health and hence reliability and usability of the signal out of even the noise portion of the signal they're delivering. So these are smart instruments today. On the actuator space, I think we're seeing a wealth of more dynamic actuators before. Also, actuation has become more affordable and more widespread, and there's new types. And in particularly, both for industry and utilities, though I'm a control engineer by training, I have to say I've really very much become a friend of power electronics as a discipline that is very close to control, relying on control, and highly useful for closing very dynamic control loops. There is communication. I think we get so used to the yearly improvements in communication, we take them for granted, but I think it needs to be mentioned that there's lower latency communication, higher speed, it's more affordable. There's wireless, which allows us to also put sensors in places that we wouldn't think about before. But there's also all these many standards, which at times can be a bit of a headache, because having fewer of them would make connectivity easier. There's processing. Again, we take it for granted that every time we buy a computer, it's at least twice as powerful as before, more affordable, but also these things are more short-lived, and I think that's a challenge also for us doing automation, where usually an automation system is designed to live with a process plant or a utility installation. So actually the design lives increasingly mismatch with each other. And finally, many of these technologies are increasingly integrated. So if you see a box somewhere in industry where you used to say, okay, this is a PID controller, it's a nice box, it has the relevant buttons and labels, and that's it. Today, actually, increasingly, you find things integrated, which has a number of opportunities by itself, but which also means that we as a community don't actually always count them as control when we first come to them. Getting back to the power grid, I'll start with a couple of comments on the power grid. I have to mention that when I studied electrical engineering myself, I got rather attracted to automatic control. It was the most fascinating and in some sense the most difficult subject you could choose, and I think that many of us have that in common. And if you would have asked me about why did I not choose power systems or high voltage technologies, I just thought this wasn't moving anywhere, and it was a relatively stationary subject. And this is one of the areas where I freely admit I was wrong. I'm still happy I went into control. But if you look at these challenges that the grid has to confront, if you look at electricity consumption growing at twice the rate of overall energy, and that from a 20-25 year perspective, we are seeing doubling and tripling in China and India. If you think that in our modern society, we increasingly rely on electricity, commercially and in private life. Think of the consequences of not having electricity. The price is rising if we don't have it. And also, it is power generation, i.e. it is the electricity grid that stands for the largest share of CO2 emissions. So also there, I think there's a clear call to action here. So since we're in Italy, I'll quickly cover a couple of topics, and I thought I'd pick an Italian example to say why do I think power systems are interesting for this community. What you see here is a couple of minutes from September 28, 2003, and you see a curve how frequency, which in this part of the world should be 50 hertz, is actually dropping because a tie line is lost, so 7,000 megawatts of imported power are suddenly not there anymore, and you see a stability challenge taking its way, ultimately ending in a blackout. So power system stability is definitely a large-scale control challenge, and for a number of reasons, including the increasing intermittency of the many renewable sources that are increasingly brought to the grid, power system stability is not something we should take for granted, but it is actually something we should work on and really progress in a significant way. And at the same time, when we look at power systems and control challenges and stability, we should acknowledge that already at the very local level of a single generator, if you have a disturbance and you resynchronize a generator, how will the transient be dampened? One of my colleagues has prepared this case just to illustrate a well-tuned and a not-so-well-tuned generator control, and you can see how it synchronizes or how it actually fails to synchronize. When we mention here FACT devices, flexible AC transmission systems, these are power electronic devices that today, as new actuators, we have available to actually enhance this situation. I'll get back to that a little bit. Also, in the local level, we often take sort of limitless bandwidths and fast real-time execution for granted. But these are, of course, some very fast dynamic processes. So you can see here a disturbance that is introduced, and if you can actually clear it within 100 milliseconds, then you're okay. But if you're taking just a little bit too long, 170 milliseconds, that disturbance is actually running away, and there's no way you can catch it again. The new actuators I was briefly touching upon, really power electronics, i.e. the switching without movement with 50 to 10,000 and more times on and off per second with relatively low losses. So the principle that you can use to go from one AC frequency to another controlled frequency, or what you can also use in a whole range of other industrial, like variable speed drives, or utility like flexible AC transmission systems, high voltage DC transmission systems. This has been a technology area that's been advancing tremendously. And this is basically offering us new ways when we want to go and control the flow of power through a corridor. Basically take this hydro plant here and take a big city on the other end, and let's simplify that to be just one corridor where you have the voltage and phase angle here. You've got an AC line that you push the power through, and here in parallel we've got a power electronic converter from AC to DC, a direct current transmission line, and then going back to AC. Then actually, if you look at the power flow equation, the classic methods of power engineering from half a century ago are basically series compensation, and they are phase shifting transformers, relatively stationary assets that you deploy sort of very gradually. At the same time, we've got these new components that we are closing very different loops with today, and that's static VAR compensation. So that's basically power electronics working on controlling the reactive power and the voltage levels. And we've got voltage source converter, high voltage direct current, which is basically a very controlled pipeline in parallel to this one here that gives us a great way of controlling the flow of power that just wasn't there. If you look at the curve here on the right-hand side, then you see voltage source converter, high voltage DC technology that in ABB we call high voltage DC light. That's the technology we are using for power undergrounding, for subsea power cable transfer over long distances where AC would run into reactive power problems. That technology around 2000 was barely visible on this chart. We look at transmission power here, so we were at maybe 50 megawatts around the year 2000. Today, in 2011, we've actually reached more than 1,000 megawatts transmission capacity per high voltage DC. So actually, if you compare this curve to many of the curves you see in IT or communications, it's running up as steep and as fast. So that's one of those curves that I've had the privilege of being a part of driving this up, and at the same time it's helped me revise some of my prejudice on the power side. It absolutely is a very fast-moving discipline, and I think it's a close neighbor to control that enables us to do many new things. To show you sort of the level of deployment this has reached in industry today, on the left-hand side here, you see a link between Norway and the Netherlands, and this is 700 megawatts of power through a 580-kilometer subsea cable. And what this does is the Netherlands basically have a fairly peak profile of electricity consumption during the day. Norway has a lot of hydropower, which still happens to be by far the best way of storing electricity, is actually in the form of hydropower. So every day during peak time, Norway is exporting electricity to the Netherlands, which doesn't have a lot of elevation gradient to store electricity as hydropower. And every night, since there's excess nuclear and coal power in the European grid, that is exported back to Norway. So in some sense, you could say this has created the world's largest storage solution. And it's been in operation since 2008. At the same time, high voltage direct current is being used for integrating and enabling all these remote wind farms. The North Sea in this area, about 100 kilometers, a bit over 100 kilometers away from shore, is still only 30 meters or so deep. So a lot of new wind farms are being built there because the water depth is manageable. The wind is very reliable there, and actually also the windmills are a bit out of sight and out of sensitive ecological zones. So since 2009, this 400 megawatt power transfer is working. Why am I telling this to this audience? Well, it's basically because this is a very powerful new actuator. So in this simplified picture that a colleague of mine put together for me, what you can see that again, you have an AC line, you have a DC line in parallel just at 10% of the rated power of the AC line. And now, how do you deal with the control of disturbances here? And basically, 3 control strategies are shown here. And I want to emphasize these are not just control strategies in the sense of, okay, it would be trivial to just pick the best among them, but these are 3 different control strategies played on a voltage source converter in this case, which actually means if you pick an active power modulation, so you just look after active power and ignore reactive power, what that does for you is it does the conventional high voltage direct, what we call classic, that's line commutated converter control, which is much more limited. So it's actually also implying what could I do with an alternative actuator, which would be a classic high voltage DC line. If, on the other hand, you say, let's just forget about active power management for a while and concentrate on reactive power, that would be the same as using one of those SVCs that I was showing in the power flow equation picture earlier. So it's again sort of trimming it down to one device. And here, of course, it's not just the control strategy, but you're making full use of a meaningful control strategy and an actuator that's able to execute it. So in a sense, you're comparing actuators and control strategies here. And I'm not going to spend time on the equations. I'll make the slides available. I think those of you interested in this particular area would anyway find them relatively obvious, but I rather show what is more easily read in such a plenary, and that's basically comparing the different control strategies where you can see that this mixed control, which makes use of active and reactive power, which is what a voltage source converter, high voltage DC line embedded in the AC grid gives you, that you really get the best transient response, both in terms of machine angle as well as in terms of the sending end AC voltage. If that now all creates the impression okay, so there's been this wave of technology and it's slowly maturing. I think quite the opposite is the case here. We're also seeing new sensors in the grid. They're called phasor measurement units, and what that means is geographically distributed. You take time-stamped measurements of voltage and current and the phase angle between them, which suddenly gives you, for a whole country or even larger areas, gives you a distributed picture of the stability situation and constraints in the grid, which also then enables you to actually start thinking about closing new loops. Today, if you have one of those SVCs, so a power electronic control device at one place, and you're looking at inter-area oscillations in a grid, then today's strategy is clearly you control this locally based on the signal you have available locally. And these phasor measurement units that I was mentioning, introducing them, which is a process that is going on out there, that means suddenly you get a distributed picture of stability, which today is actually used for stability monitoring. So you can, for instance, think about operator screens where areas of a map are getting colored, and you can see, okay, we're getting close to a stability situation that we need to manage. At this stage, managed manually by operators. So this is not an automatic control loop just yet. But with these FACT devices and the phasor measurement units, a lot of work has been going into closing this next loop and saying, can we not, rather than provide all this information to humans who then do the processing, can we not run this automatically and improve the way we run the power grid here? So that's really work in progress as we speak. And I think also that is just an in-between step, in the sense that towards stronger and smarter grids on the transmission side, you really see Europe becoming more stitched up with these DC links that I was mentioning before. This is all happening as we speak. Many of these are in place, others are under construction. China is putting massive high voltage direct current capacity in place. The largest that we built and current world record is 2,000 kilometers with 6,400 megawatts of power. So that's basically the average power consumption of Switzerland through a single line. So this really does change the way the power grid is operated and can be controlled. And then, of course, here in Europe, there's a lot of discussion and work to see how could we move towards a vision of what we call desert tech, which is basically based on the fact that the world's deserts receive such abundant sunshine that you could, in some sense, technically easily power the entire world, but of course at what cost? So the question is, how would a meaningful grid and power generation scenario look like that over time would get us towards this? This will mean multi-terminal DC links. It will mean multi-taps in the DC space also. And it will mean, over time, DC overlay grids and mixed AC and DC grids, for which basically you get thrown back 100 years to the days of AC versus DC, only that today it's AC and DC, and you have to face the question of how do we actually control and protect these new structures for which the old textbooks don't give us the algorithms. This was the transmission grid, and I'd like to shift gears and get quickly to the distribution grid. Basically, the distribution grid is simple, and it's called distribution grid because it distributes centrally generated electricity. That's the paradigm. But of course, as we start adding local generation, you have a microturbine, you have a small windmill somewhere, you've got solar power on your rooftop, you do initially reduce the boundary flow into the system. So actually, initially, there's just less load on the distribution side, not a problem. But as you add more generation, at some point you will have to think about voltage controlling this system. Previously run open loop. Now there's a need for control. and actually also a need for different protection around it. As you still add more generation, at some point you reverse the power flow. So it'll be a distribution and collection grid combined, which raises the next challenges of dealing with fault currents and dealing with reactive power. So there's more control to be done here. You introduce storage, which then also allows you to actually think about islanding the whole thing and running your grid independently, in particular considering demand response, demand participation, where you prioritize some of the loads against the right criteria, which is a non-trivial topic in itself, and I'm sure Paul will go into it in his plenary lecture more. And if you look at it, this is an evolution. All the black things that we have today, they're still there, but there's an awful lot of blue that is new to this grid, and there's an awful lot of new control challenges that is new in this grid, which I think represents a tremendous opportunity for this community to make a contribution. As sort of an industrial company, of course, we're not just making concepts in this space, but we're actually also actively trialing concepts together with partners in a number of places. This is Stockholm Royal Seaport. It's got about 10,000 households, and together with Fortum, which is the local distribution utility, we're actually putting all these things together and experimenting with these things for real to actually see if the concepts work. Give you an interesting example of something we still caught in the study phase beforehand, but if you think of electric cars, you should think that's not so difficult as long as only 1 or 2% of the population have electric cars. That should not be a problem. But what we found in a more detailed study, interdisciplinary study also, was that actually the electric cars are not uniformly distributed throughout your grid, but actually they tend to clog in certain neighborhoods. Your neighbor has one, so you also want one, and there's also obviously wealth is not evenly distributed, so there's parts of town where people are just in an easier position to buy one, and then very quickly you both get primary technology changes, which can be fuses or distribution transformers blowing, but they can also be control challenges because the distribution grid is being taken into modes of operation that it was never designed for. You get interesting new challenges even without those electric cars, and basically some of my colleagues helped me here to pose this as a control problem. If you look at the task of minimizing the grid losses and peak power demand, because peak power demand is something that carries quite a cost as well, subject to the power flow equations, and there can be an unbalanced multi-phase system, and you see a map here of a system which actually happens to be the case that they've deployed it for, together with a US utility. You've got voltage constraints, you've got current constraints in all these devices, you've got operational constraints on your different actuators. They can be tap changes, they can be capacitor banks. Then you end up with a mixed integer nonlinear program that if you solve it in real time, you can gain quite a bit of advantage. Show you how this normally works in the traditional world. You've got actuators here, for instance, this capacitor bank. You've got the lords, some houses and offices, and you've got actuation here. Also an OLTC is an online tap changer. Sorry for the abbreviation. So if you then look at voltage and how basically voltage drops over the line, and then you get profiles like this between the max and the min. So you have to stay in this range in order to make sure the last household on that line gets enough power, and in between you're not violating any of the voltage or current constraints that would put your system out of operation. Now in the new world, you've got all these new sources of generation, potentially storage, in addition to the loads here, and some of the loads are also controllable in themselves. So actually you get the problem of not just controlling everything based on local signals, but you're actually with the possibility of now smartly connecting information under the heading of smart grid on what's going on in your grid, you can actually do a coordinated control to keep it within the constraints here, and then also use that coordinated control to bring down the losses, i.e. to go somewhere here near this minimum voltage level without violating the constraints. One of the big factors here is by managing your reactive power properly, which doesn't help your consumers, but that loads the grid, and that today on the level of the distribution grid is rather empirically managed. So a capacitor bank is maybe switched in at 7 in the morning and switched out at 8 in the evening or something, rather than switched based on the actual current and voltage measurements in the grid. So great opportunity here. And in the first project where we've deployed this with a US distribution utility, we've achieved in the order of 2% savings with this strategy, which is quite an amount if you think of the power that a utility is providing. If I sum this up for the power side, basically we're moving from a grid that is very hierarchical to one that still has the old elements but grouped in new ways. I think if I can sort of somewhat sloppily call it moving the electrons, a lot is changing on the power technologies and actuator sides, the power generation, all the windmills, solar panels and so on, but also the power electronics as new actuators. So I think this, in some sense from a systems point of view, obviously they're contributing power, but they're contributing from a stability point of view initially disturbances, but you also actually get to counteract them better. You get storage increasingly in the grid and a need to actually have and manage that. And on the other end, you get the sensors and improved communication with the smart meters, phasor measurement, new communication standards, and also wireless helping us in there. Moving over to industry, I said I consider the energy challenge really an overarching challenge for all of us, and certainly for not just utilities but also industry. If you look at the energy intensity of industries, it's really a significant amount of energy that is going into these energies, distinguished here by electrical and thermal. And if you realistically look at any of these industries, the potential to improve profit in these industries by controlling the energy consumption right is actually very often in the range of the actual profit they are making. So we're talking about very significant amounts. So it's a rather attractive proposition to industries, and a lot of investment is happening in these areas. Something that maybe in this community where we look a lot at advanced control, we might not all have on the radar, but I think is personally very important for the discussion about what's the impact of control, is the variable speed drive. I think easily this one box, the variable speed drive, which actually isn't called a controller, but it's sensor, actuator, and controller in one box, that has a great contribution to global energy questions, as well as actually to improving industrial productivity. And I think a good part of that is due to control. If you look at the alternatives, pumping a fluid, for instance, in a plant, what's often happening is you've got a fixed speed motor. Basically, you've got a throttle valve then as a way of controlling. From a control point of view, that's not even so bad. You get reasonable control, but this is very poor in energy efficiency. You're putting the energy in here, you lose it here. There's bypassing, which is slightly better, but not a lot. There's on-off control. So in some sense, manually, the thing makes too much flow, so you say, okay, I switch it off now and then. Only works if you've got buffers. Otherwise, this is usually not really a meaningful strategy. But with variable speed drives, basically you move this to closed loop control. So you bring it to just the speed you actually need for the process, which normally comes with something like 30 to 50% savings on the energy side, as well as better quality and reliability of the product and the process plant. Today, there's about 10% penetration. If you do the math, 50% of global electricity is today consumed in industry, 2/3 of that in motors. And if you look at today already 10% penetration, you can say, wow, actually drives, and in those drives control is already making a very sizable contribution. If you look at it the other way around, you can of course say, well, there's actually 90% further potential for penetration. And I think it's good to be able to look at this from both perspectives. Just quickly on how this is impacting industrial productivity. The first two here, pump control, fan control, there's literally thousands of these examples where you just go, you put in standard technology. It's not very sophisticated, but you go closed loops where you had open loop before. You put in closed loop with the variable speed drive, and you get tremendous energy savings. These are really just examples from very, very long lists. On the other side, you also get sort of, I'd almost say, engineering miracles that you can also do with this as a building block for a rather new concept. So what you see here is an offshore platform in the North Sea, offshore Norway, which basically, Norway has essentially hydropower, so it's very clean power there. So in order to actually run the gas compressors on this platform, you bring in high voltage direct current from shore, and then you immediately use the receiving terminal as the drive for some very high voltage motors. So that is actually a device that in a combined way executes a high voltage DC receiving terminal as well as a drive control function in one actuator, so to say. So that's rather neat, and it's been running since about 6 or 7 years now, and really been a benchmark in the industry. Or you get ship propulsion, where rather than running the diesel engine, a mechanical shaft and the propeller, you can break the loop and say, do away with the mechanical shaft, you run the diesel at the best operating point, then you run a cable to an electrical outboard motor that is then of course also controllable in a very different way, which gives you better maneuverability on a ship, and also anywhere between 8 and 15% energy savings. This is a double propeller arrangement even, so these two are counter-rotating, so you gain new degrees of freedom also hydrodynamically here. Switch over to a bit more traditional control, and when I say traditional, I want to start with this gentleman here. He's one of our ancestors. I've not been able to precisely date this picture, but it's definitely more than 110 years old. And this guy actually is working with his control system here. So he's got a couple of signals here. He's got his actuators, as you can see. And in some sense, what's interesting is he also switches electric power directly. That's not something you will find in the control loops of future generations. So if we move on in time, this is middle of last century. So this is the days when Ziegler and Nichols found their famous tuning rules for the PID controllers. Then with the Taylor Company, one of our ancestors. So this could well be one of their control rooms from those days. If you move on, this is 1970s in a German chemical facility. You see all these discrete controllers and recorders. So everything is a box, and what is a block on a diagram is basically a box here. This moves on. This is in the 80s. You see the first color screens. This is a US refinery in the mid-80s. And if you move all the way, then basically today's control rooms, though much larger than what you can see on this picture, this is just a demo picture, so you have many more screens in the large ones today. Basically, you have many things that go beyond the classical functions of a process control system. For instance, you also may manage your maintenance crews from here. You may manage some of your commercial interfaces through here. So if I put all these photos on a trend chart and look at, on one axis, the breadth of domain, i.e. how broadly can you scope your system versus the number of input-output points, then I'd see a trend like this. So actually, initially you go back, you concentrate entirely on process control. You scale this up in a major way. And I think here it's really where all of us, we owe big time to the development in the information and communication technologies that have taken so many of the bottlenecks away that we were confronted with earlier. When we wanted to do advanced control 20 years ago, you could very often say the industrial control systems don't support it. Today it's basically almost limitless, where you can actually interface with all sorts of functions, where you get real-time stock market prices for the product you're producing. The spot market in refineries, for instance, has a major influence on the production mix. But also in a lot of the other industries, the spot prices on power influence how you run your production. These are things I consider here under breadth of domain. That, of course, has helped us in removing these constraints for deploying control. We are certainly deploying an awful lot more model predictive control. And I think I'd be preaching to the choir here if I would now go through the advantages of model predictive control. But I'd like to highlight that certainly energy consumption explicitly included as a cost or constraint is something that we industrially really also increasingly do and see. One of my colleagues has kindly given me this picture, which is basically showing sampling time versus the complexity of applications, and how over the years the frontiers of technology are basically moving. So you can see chemicals and also refining, though very demanding, have been early movers in this space. But today you can really see we are penetrating more and more the other industries, and we're in an exciting time. We're in an increasing amount of also the very fast electrical, and that is often power electronic, electrical loops are being closed using MPC. I think you all know that, of course, designing an MPC is a demanding task, but if you look at the overall work going into a project, really most of the cost and effort goes into proper modeling, because it really all stands and falls with that. And these models are, of course, also required for a host of other functions. So I don't want to spend all the time on the details of that, but in an earlier talk, I've used an example where I was actually going back to one of Karl-Johan Åström's 1960s work, because he had happened to work on a plant Gruvin in Sweden. And sort of if we look at what our ability to process and control in terms of scope has been in the earlier days, it's been more looking like this, whereas today this is a true picture from this particular and by coincidence same pulp mill that as a picture looks like this. So you can rather go for some very broad scopes and manage complexity on this level as large, nonlinear dynamic models and improve production processes. I've not been able to obtain permission to give the exact details of what this control has improved, but for this also pulp and paper mill, which is a South African case, I do have exact numbers. First of all, you can see here in optimizing the steam power relation in a pulp and paper plant, which is a major driver. You need the steam for producing the paper. You need to import or export power in order to be economically viable against a changing power price also. You can see already easily that with an MPC on, you get rather better temperature control and steam flow control, which translate to some very sizable economic contributions. These are numbers per year, so you can easily see an impact of $1 million on a single project, and that is what is driving modernization investments in such projects today. Staying in pulp and paper, I mentioned that this is an industry that is particularly sensitive to the cost side. You can see a super calendar machine. This is basically lots of rolls and heat sources. Heat sources with a profile that are shown here. So in control, from a control point of view, your controllable devices are the steam boxes and induction zones. and you've got these rolls in between, and you want to make nicely glossy, high-quality paper. So this is a rather large M by N linear quadratic problem with 600 times maybe 300 matrix elements. And I hope this, yeah, sorry for that. This is a bit hard to see. So take my word and take the text here. But basically you can see that the caliper, the top gloss and the bottom gloss, which are all qualities that have a significant implication for the commercial value of the paper you're producing, they are benefiting significantly. The piece that looks rougher here is you're actually making more controlled use of your actuators here, so that you make a more uniform product and you save significant amounts of energy. I'll skip over the rolling example with a look on time. It is very similar, and would also like to mention here in a cement industry example, for instance, you get the same picture. You get a rather broad distribution of temperature, which is in some way a proxy for product quality you're creating in a cement furnace, while your challenge is to actually produce a uniform product with a very variable fuel, because your economics in a cement plant depend largely on what alternative fuels are you actually able to process, and they may not be the best fuels from a calorific value point of view, but you might actually be paid for burning them because they need to be burned anyway. Wireless I mentioned already. Looking at time, I'll be a bit quicker here. I just want to say that wireless around the control loop really provides ample new opportunities, and it also, in situations like this, where you would just say, it would help me so much for the tuning of my controller, for my system identification, but maybe also permanently for control, to know the temperature at tray 27 of that distillation tower. Now much easier with wireless technologies, you can actually get that information, and you can get it even to also unlock information that is stranded today. You have many smart sensors already that have a microprocessor, but they're on a 4 to 20 milliamp connection, i.e. they can only say the temperature here is so and so, and even if the sensor knows I'm actually broken, I'm clogged, the noise level is not right, it can't tell the system. Here with wireless, basically you're getting a parallel path that helps you make this advanced diagnosis. Also, you get new levels of integration where I'd go and be a little provocative and say power and automation converge, in quote unquote, because I know convergence has a very different meaning for many of you. But if you look into many of the large energy intensive plants, basically they have a control room for process and a control room for power. They're completely disjoint. Whereas if you need to know how much can I get more power in for a certain production scenario, can I overload that transformer a little more, or is it temperature limited right now, then you need to run an extra wire and put a temperature transmitter into that. In these new structures and with these new standards, you can actually just query the object and ask, what is your overload ability? So this would contain the sensor, this would contain the model, and you could, on a much higher level, actually interact between the automation and power. So you can get the same operations interfaces, you can get a plant-wide sequence of events for removing causes of failure, and you can standardize and integrate, which also means you can close loops that previously were just not realistically closable. If you extrapolate that further, in the oil and gas industries already today, we're running in setups like this, where offshore you've got a subsea portion, you've got the platform, you've got communication, and you've got an onshore operations center often dedicated to this platform, but sometimes supporting different platforms. And you've got suppliers like ourselves supporting that center. You've got experts on remote. So I think also here we really have possibilities to close entirely new loops. I'm not sure yet about sort of the latest consumer electronics that many of us are playing with in our free time. But also thinking about those, I mean, it's fantastic to actually be able to walk around with something that has so many sensors built in, so much processing power. So we're actively fantasizing at this stage of what else could we be doing with these new gadgets. All that should be taken with a bit of precaution. Obviously, the power system that I talked about, the industrial plants, these are real-time mission-critical systems. They have rather different needs than our phones or laptops, where we just reboot the thing in case of an issue. So one of the increasing tensions on us is, on the one hand side, to follow and make use of the most recent advances in information and communication technologies that I praised earlier, at the same time as making it something that's proven, hardened, secure, if you think of the Stuxnet incident about a year ago. And then, of course, also think about, do I solve this with a box, which, like a variable speed drive, like a robot, for instance, also may well contain many control loops, but sort of once it's built, you don't talk about the control so much anymore, so we're here at the hidden technology again, or whether you actually put sort of dedicated control just for this specific plant in here, which is, of course, a lot more costly, in particular because of the modeling. I mentioned robots, just want to quickly touch on this area. It remains a fascinating area, obviously, but I thought towards the end of this talk, I'll just rather do a video summary. Let me see how I advance to the next slide here. Like this, yeah. So in industrial robot controls, it's been really, industrial robots wouldn't exist without control. So there's been the classic objectives of cycle time. You just want to produce something in a faster cycle, which means even with a heavy load, like you have a weld gun, and you need to move that arm there very quickly, but without actually bouncing into the object you're trying to weld. So that's obviously quite a fascinating control problem. You got weight reduction, so some of the stiffness, rather than having it mechanical, you want to, as in the video I was showing earlier, you actually want to move that to control and have savings as well as have better dynamics. And of course, path tracking. These are some of the original shots from the early days of what we call true move. So independent of payload and moving speed, you actually get lines that you can't distinguish anymore. So these are obviously before that. It's all model-based control, high-order gray box models. And more recently, there's a lot of applications where you need sensors like force control, coordinated multi-robot control, and higher degrees of freedom, and robots and people working together. This is a tracking case. I skip over that now, if I can. And of course, then all these robots are actually working together. These used to be dedicated machines before that were just framing stations building cars. Today, this is all flexible automation with robots. That's because we've been able to close the loop on those. That gets me to the wrap-up part. And that's just 3 slides. One, I do think power and automation increasingly converge, both because of the user needs as well as the technology capabilities. It's becoming more and more interdependent. In industry, people are looking at energy efficiency and productivity combined. In utilities, people are looking for a stronger and smarter grid. And I think all these are challenges that force power and automation to work more closely together. And I think for us as control people, it really means this deserves a closer look. Second, on the impact control, I think that the impact of control has been, and also will be significant. I think we too easily overlook the things that control contributes in products. It's the cars, it's, in our case, the robots, the variable speed drives, that make such a huge contribution already, of which a significant portion is control. And of course, the many application control solutions come in addition to that. But the impact wouldn't be nearly as big without those neighboring fields, the IT, communications, and power electronics. So we are interdependent, and it's not so easy to isolate the impact. And my third conclusion, I think generically, if you look at innovation, my simplest definition is one of the three needs to be new. A new problem, a new solution, or a new match between a problem and a solution. And I think finding the right problem is as important as finding new solutions, and that's much easier done together. So I really see control as a team and contact sport. And I think also I want to add that from my industrial perspective, innovations that reduce costs are at least as hard and important as those that increase performance. And with that, I'd like to close by thanking you for bearing with me, thanking you for this invitation, and thanking you also for the many things you have taught me, many of you directly in personal interaction, many others with your books and articles, and in particular thanks to Manfred Morari, who's been a phenomenal, not just thesis examiner, but also mentor and increasingly speaking partner over time. Thank you very much. Patient wait.
Dr. Terwiesch presented the industrial deployment of control in general, using many practical examples. Also, the need of cooperation of the other technology and number of the direction for the futures. The material and videotaping will appear on the Ifac website from general support of the Congress organizer. Let's give him a big hand for his excellent presentation.
Thank you.